Welcome back. Here we're going to do another example of the binomial experiment. So the one we saw before, it's very simple, not a large number of trials. And so for this one, we're going to see a larger number of trials where we need stat crunch to help us calculate the probabilities. And also we'll present it within the context that you may see it out in the field. So in the study that we're going to examine, they want to know whether babies could recognize good and bad behavior. And so what we want to know is, we present babies maybe with these two types of toys, and they're one's exhibiting good behavior and the other's exhibiting bad behavior. And then we present the toys to the baby, and are they more likely to select the good behavior here? And so, and in studying the outcomes of this experiment, really, it's going to follow a binomial distribution. Okay. Somehow we're going to get a binomial distribution. So, just to show us an example, let me just show you the design of this study here. Okay, before we get started. Okay, so let's watch this here.
Developmental psychology called theory of mind, which involves basically asking, how do we develop an understanding of other minds? How do we come to understand other people's thoughts, their relationship between their thoughts and their behaviors?
If you both want to do different things, what could you do?
How we reason about other minds in the world.
Peekaboo!
They began addressing some of these questions with infants.
In this study, parents bring their 6-month-olds into the lab.
At the other side of a long table is a hill stage. A red circle guy with googly eyes tries to climb the hill. He sort of goes up the hill and then falls back down. He always fails at it. Then a blue square character, also with googly eyes, comes from the bottom of the hill and bumps him up to the top of the hill so that he's successful. On different trials, the climber tries again to get to the top of the hill, and then a yellow triangle character comes down from the top and bumps him to the bottom of the hill, so prevents him from getting his goal. Babies see this a number of times until they get nice and bored with it. So we stop and basically do a choice measure. Moms are asked to close their eyes.
So really quick, why would you think moms are asked to close their eyes? Okay, remember, this is a controlled experiment, right? We want to actually say whether or not these babies can recognize this behavior. So we don't want our data to be biased, right, or results to be garbage. So, we don't want mom or in any way, shape, or form to be like maybe pushing her baby towards the helper toy or something like that. So that's why we're having her close her eyes.
An experimenter who did not see which character was which brings over the two characters to the babies and just sees which character the baby touches first.
So one other thing is that the person bringing out the toys, they did not see the study, right? And that's also very important. It's kind of like the blind part, right? For if you about blind study. So the person who's going out and giving the toys, they didn't see it, because if they did see it, maybe they know which one is the helper, which one is the hinder, and there may be something in how they're moving and how they're acting where it may make the baby look at the helper toy or something like that, okay? Or we don't want them to bias the study anyway, so that's why the person bringing out the toy didn't see which one is the helper and which one is the hinderer.
What do you want?
We found that, impressively actually, almost 100% of babies preferred the more.
So that's more or less how that was set up, and so one thing to note here is that the research question here was, can 10-month-old infants recognize good versus bad behavior? And are infants more likely to favor the good behavior? Okay, so and then we say, well, how does this translate to what we'll expect to see in our experiment with babies selecting helper or hinderer toy? So what we're kind of saying here is that each selection made by the baby is like a coin flip. right? Either they select the helper or they select the hinderer, right? And pretty much for a sample of babies, we're going to count the number of times they select the helper toy. So this is much like a binomial experiment, right? We're counting the number of successes out of n-fixed trials. We're counting the number of helper toys selected out of the total number of babies in the study. Okay, so just note that if the research hypothesis were true, then baby will be more likely to select the helper toy than the hinderer toy, right? Because they're saying yes, the babies do in fact recognize the good behavior, and they favor the good behavior, so therefore they would be much more likely to select the hinderer toy. Okay, but in our study we won't assume that. We'll just assume no preference, like 50-50. Okay, kind of just like how we did with kissing the right way. We're saying tilt the head to the right is 50-50 chance. So some other things to notice here is that, this is pretty much a controlled experiment, right? They're being very, very careful to eliminate other types of variables. So one by one is the mom, right? Are we really measuring if the babies recognize behavior, or we're just measuring, how much mom wants their kids to do well, okay, and to be recognized as good or something, right? And also the presenter, right? They did not see the experiment, right? So when they bring out the toys, they themselves do not know which is the helper, which is the hinderer, right? So they can't bias the study in any way. So whether it's intentional or not, okay? So here, other things that they did as far as for the experiment is that methodology section states that for 10-month-olds, the climber was a yellow triangle, helper and hinderer were red square and blue circle, counterbalanced, right? So in what we saw, the hinderer was the yellow triangle and the helper was the blue square, and the climber was the red circle, right? So you see here they're saying red square blue. So what they're saying in counterbalance, what they're saying there is that the shapes and colors were all switched around, okay, meaning that sometimes the helper was a blue square, sometimes it was a blue circle, sometimes it was a yellow triangle, sometimes it was the red circle. So they always switched the characters around, okay, because the reason they did that is, we don't want babies just to select the blue square all the time. If we would have kept the helper as the blue square every time, then maybe the babies don't observe the behavior. Maybe babies are just drawn to blue, right? Maybe they just love the blue color in comparison to yellow and red, right? It's more soothing, it's not as bright, right? Maybe they like squares as well. So we want to eliminate that bias there. Okay, so that's what it means here. And also counterbalance were which event, helper and hindering, they observed first, right? And the positions of helper and hinderer when presented to the infants on left or right. So meaning like first they would see in the vignette, we saw first it was the helper toy and then it was a hinderer toy. Well, maybe, the attention spans of babies are very, very short, right? So they're only going to pay attention to the first part of it. So it's very important that for the next video or for the next show, we have the hinderer go first. We see the hinderer go first and then the helper, right? So we counterbalance there. And then of course here, the position, right? When the lady came out and presented the baby with the toys, right? It's important that we switch the position of the helper and hinderer, right? Because say we put the helper toy on the right side every time, and maybe just most babies are right-handed and they're just going to use the right hand out of convenience. So really, they're not selecting the toy because they observe the behavior. They're just selecting, well, I'm right-handed. This is closest to the right hand, is most convenient, so that's what I'm selecting there, right? So these are all the things that we need to think about in these controlled experiments to eliminate the bias and to eliminate variables, right? So that we can establish more or less this cause and effect, okay? So, in this study, we have 16 babies included in the study, okay, and this guideline we'll talk about later in the class, okay? We'll leave that for later, but this is just saying we always need to compare sample size with population size, and so population size must be much bigger. We'll talk about that later, okay? All right, so just talk about the study here. So As far as the outcomes of our study, let's relate it to the binomial criteria. Well, here we have 16 babies in our study. That number is fixed. Here the responses of the babies are independent. Okay, so each baby, they go under this simulation by themselves, so the outcomes are independent. It's not like a group of babies; it's just one baby at a time. As far as outcomes for each trial, our success is a helper toy is selected, and our failure is a hinderer toy is selected. Okay, and here what we'll do as far as our probability of selecting, we're just going to assume that it's 50%. Okay, so typically we don't want to assume our research hypothesis. So I'll just say let's assume that babies do not recognize good and bad behavior. So they're just going to randomly select whatever toy. Okay, so let's just assume that it's 50%. Okay. Okay, of course, under our research question, we think that this is larger. We think that they do recognize the behavior and that should be larger. Okay, but a typical outcome, right, for 16 babies, this is one outcome I could see. Baby 1 selects hinderer, baby 2 selects helper, baby 1 selects hinderer, these babies here select helper, this one selects hinderer, helper, hinderer, helper, helper, hinderer. Okay, but in our data, remember we're counting the number of helpers, so I'm going to code it as a 1, and hinderer, I'm going to code it as a 0. Okay, so that way if I sum across all of these, I will get the total number of babies that selected helper out of the total 16 babies. Okay, but this is just one possible realization that we could see. Okay, so in the data, the researchers found that 14 of the 16 infants in the study selected the helper toy. Okay, so this is like pretty convincing evidence that perhaps that babies do in fact recognize this behavior. So one thing to think about are what are two possible explanations for this result that researchers observed. Well, the two are this, okay, is that, well, it could be that 10-month-olds do recognize helpful behavior. Therefore, they're more likely to select the helper, right? Those two that didn't, maybe they're future sociopaths, I don't know, future Dexters or something, I don't know. Okay, but I mean, that could be a chance that they do, all right? The other thing is that it just occurred by random chance, okay, meaning that, that they do not recognize the behavior, it's 50-50 chance. And so, but just by chance, we observed 14 out of 16, right? So to put this in perspective of coin flipping, it's just saying like, well, if I were to flip a coin 16 times, right, is it possible to get 14 heads out of 16 coin flips, right? That's pretty much what we're saying. Like it just occurred by random chance. Okay, random chance meaning 50-50. Okay. So let's look at this here. So what I have here, this is the probability distribution graph for a binomial where n is 16 and p is 0.5. Okay, so think about it. If there's no preference, if it's 50-50 chance of helper toy, and I have 16 babies, how many would you expect to select the helper toy? Well, if we do 16 times a half, we roughly get 8. Right, roughly get 8. So what this distribution represents, remember these distributions help us model the phenomenon, and by looking at this graph here, looking at this probability distribution graph, so remember it's not a histogram, okay, because these here are probabilities, and these are all the possible outcomes of our experiment, right? 0 babies select helper toy, all 16 select helper toy, right? But if you look here, 8 is the most common that we should expect to see, given that there's no preference. And then maybe 7 and 9, 6 to 10, 5 to 12, maybe 4 to 13, right? Maybe these, right? So these, I mean, within these range, definitely I should see, if there's no preference, it's very likely to see, 6 to 10 babies select the helper toy. Okay, so what I want to do is say, well, if there's no preference, right, and we just observed this by random chance, so what's that chance of us observing that? So what I want to do here, so 14 lands right here, right, and it kind of almost looks like maybe it's like an outlier, but it's definitely like the largest value. So I want to find out, well, what's the chance of observing 14 given that there's no preference? Okay, so what I'm going to do here is I'm going to find the probability, right? I'm going to find the probability right, I want to know if this number of 14 babies if it's significantly high. Okay, so we're going to talk more about this when we get into inference, but I want to find the probability of a binomial. Okay, but I'm just throwing it within the context of this experiment here. So what we're saying is that, is this 14 far enough from these typical values for us to doubt this here? So what we're going to do is we're going to find the probability of observing 14 as the best worst case scenario. Really, the probability of observing 14 or more babies select the helper toy, given that there's no preference. Okay, so what I need to do here, this is probability of X being at least 14. Okay, at least 14 helper toys are selected. So either I can have 14 selected, 15, or 16. That's what we've seen here. 14, 15, 16. So I have to find the probability of each. Okay, so for each of those, I have to use that definition here, here, and here. These are the equations of the distribution. Now, we will not use these, okay? I don't want to scare you with these, but I just want to show you that here we have to count. So this is like the probability of getting helper toy for 14 babies, probability of getting a hinderer toy for the 2 babies. And what this is counting for us is the number of ways that 14 babies out of 16 can select the helper toy. So it counts the total number of combinations here. And if you were to calculate that number, we would get 120. Okay, so there's 120 scenarios where 14 babies out of the 16 select the helper toy. All right, so imagine doing that by hand. No way, no way. So that's what this thing is doing. But don't worry, we won't have to use this here, okay? But if I were to find this probability, it'd roughly be 0.0002. So roughly a 0.02% chance of observing this by merely random chance, right? So really, that's a very, very small probability. What it's telling me is that, assuming that there's no preference, these are the number of outcomes that I should expect to see of babies selecting the helper toy. But I observed something all the way out here, 14. That's very, very unlikely to occur, right? So I'm doubting that P is 0.5, okay? And I'm suspecting that it is much larger, right? So just to show you how we would calculate this in StatCrunch, we actually have a binomial calculator. So I'm gonna go ahead and show you that really quickly, okay? Okay, I'm gonna close this down and let me go to Stat Calculators Binomial. Okay, so here what I want to do is I want to find this probability. So I have 16 babies. Okay, and one thing that's neat about StatCrunch, if you're not sure what goes here, just hover your cursor there for a second and then see a little box comes out. It says a number. Here. If you hang it over here. Okay, if you hang it over the field that's empty, it'll give you a definition, probability, a number between 0 and 1. So it kind of gives you the output for each field. Okay, but here I have 16 babies. We're just assuming that there's no preference. And here I want a greater than or equal to probability. So if I click here, I click there, that's greater than or equal to. And then I want 14. Okay, 14. So let's compute it. Right, so if you look here at this probability distribution function graph, we get the same thing that we saw before, right? This is 8, and so out here is 14, 15, and 16 didn't even make it. But if you calculate that probability, you roughly get 0.002. Okay, so a 0.2% chance. So something very, very, very small, very, very unlikely that we observe this quantity here. Very, very small and very easy to do here. Okay, so ideally for when n is larger, like 16, we're definitely going to be using StatCrunch to find the probability. Okay, so we're not going to use these here. Okay, so don't be worried about that. But I'm just trying to give you a gist as far as what that stuff is telling us. Okay. So anyways, so in the end, we say, hey, well, it's nearly impossible to observe 14 and 16 babies select helper toy. Okay, assuming that there's no preference. Okay, assuming that there's no preference. It's very weird. Okay, so therefore we would conclude that babies do recognize nice mean behavior and are in fact drawn towards the nice behavior. Okay, so So this example is just a really neat example of the binomial experiment. I mean, really the lesson here is just how do we find these binomial probabilities, and here we're just giving an example, and then of course here we're just showing how we do that in StatCrunch. That's the real given binomial, can you find the probabilities, but we present it within this context and just revisit some important some important little kind of Easter eggs involving design of experiment, because we're saying, well, these controlled experiments, you have to be very careful if you want to establish kind of this cause and effect, and that's kind of what we're doing here. And so so just mentioning of counterbalance, right? Everything's counterbalance. That's kind of important things we do to make sure that our data is good. Okay, but that's all I have for chapter 6. Okay, so after this video we would have completed chapter 6. The next video I'll post up will be on chapters 7. Okay, but hope you all have a good day, and we'll see you soon. Bye.